Hello, this is Miss Townsend. I am just making this little video to help you to get started on the series solution about a regular singular point extra credit assignment. If you go to our Blackboard site, on the left-hand side in the navigation, there is a link that says extra credit opportunity. There you will find these lecture notes over series solutions about singular points. They're based on a section in the ZIL textbook, a very old edition of the ZIL textbook. I think it's been updated in the ZIL textbook since then, but it gives you some definitions, and it talks about sometimes what's called Frobenius's method or the method of Frobenius for finding solutions about a regular singular point. So this is actually your assignment. You're going to solve these problems and answer the conceptual questions in much the same way that you would answer conceptual questions and solve problems for your written homework. So you answer the 3 conceptual questions, and then you're asked to solve these 3 differential equations. For each of these, t equals 0 is a regular singular point. So we'll be able to use the method of Frobenius or Frobenius's method in order to find the solutions to these equations. So let's go through a little bit. I'm going to skip over this. I think you can read it. It tells you what a singular point is, what makes a singular point a regular singular point. And then it talks about the method of Frobenius. So Frobenius's method says that if t equals t naught is a regular singular point of the differential equation, then there is at least one solution of this form. And when I'm looking at this, I mean, I know we've got a lot going on here. I'm focused on this expression right here. Like, this is a simplified version of this over here. So we're saying y equals the sum as n goes from 0 to infinity of a sub n times t minus t naught, where t naught is a number, it's that regular singular point, raised to the n plus r power for some value of r that's to be determined by us. Now, for all of the problems on your extra credit assignment, the regular singular point that we're interested in is t naught equals 0. So what we're going to have is y equals a sub n times t to the n plus r, and we're going to have to figure out what r is. Okay. So you get at least one series solution that looks like that. Now, depending on the values of r, which come from setting the coefficient of the lowest power of t on the left-hand side of the equation to 0, assuming that a naught, that first term in our series expansion, is not equal to 0, and our t value is not equal to 0, there's going to be an algebraic equation, a quadratic equation if it's a second-order differential equation involving r. That quadratic equation involving r is called the indicial equation. You're going to solve for r. You're going to get 2 roots. Those are called the indicial roots, or exponents at the singularity. And then you'll have 2 linearly independent solutions depending on the relationship, you'll have 2 linearly independent solutions, but they're constructed differently depending on the relationship between the 2 values of r, which we'll call r sub 1 and r sub 2. There are 4 cases. We're only going to look at 3 of them. The 4th one we are not covering even in our extra credit assignment. So if the difference between r1 and r2 is not an integer, then you're just going to follow the method twice. First, you'll find r1, or first you'll solve the indicial equation. You'll realize that r1 and r2, if you take their difference, the difference is not an integer. And then you'll say, okay, well, if the difference is not an integer, let's let r1 be one of those values and solve for a sub n. So you'll plug in r1 equals, let's say 3. And then you will substitute into this equation and you'll solve for the coefficients. And then you'll do the whole thing all over again when r2 equals some number that is not, if you subtract it from 3, it's not an integer. So some non-integer value of r would be over here. And so then you'll solve for the b sub n. So you'll have one series for y1, one series for y2 with different coefficients, which we're calling a sub n and b sub n. And each of those is going to involve a different exponent. It'll be n plus r1, where r1 is a number, and n plus r2, where r2 is a number, and the difference between r1 and r2 is not an integer. So you're basically going to go through the method twice. Now, if r1 and r2 happen to be the same, then y1 will be constructive in exactly the same way that we just talked about. You substitute in that r1 value, and you'll figure out what the a sub n need to be. And then for the second linearly independent solution, you're going to assume that y2 is equal to y1 times natural log of t plus another series. And that series does not start with n equals 0, but it starts with n equals 1. And we're going to call the coefficients in the second series b sub n. So we'll have b sub n times t to the n plus r1, and r1, they're exactly the same. This r value and this r value are exactly the same, but the coefficients of this series are different from the coefficients of this series. You'll need to find the b sub n, and you'll be able to find the b sub n by differentiating this twice, substituting into the differential equation, and grouping terms involving this natural log of t. Now, since y1 is a solution to the differential equation, there are going to be expressions involving y1 and natural log of t that if you group them all together, since y1 is a solution, we know that when you plug that into the differential equation, you should get 0. So a bunch of terms are going to cancel because y1 is a solution. So with that in mind, after you find your y1, this series right here, you don't actually want to substitute in that series down here as you're differentiating y2. When you differentiate y2, just use the product rule here. You'll just call that y1, when we're taking the first derivative of y2, let's say. You'll have y1 prime times natural log of t plus the derivative of natural log of t, which is 1 over t times y1. And you'll keep doing that. You'll use the product rule. But you want to leave it in terms of y1 and y1 prime and y1 double prime. You don't actually want to work out what y1, y1 prime, and y1 double prime are. Because, again, those terms are going to cancel because y1 is a solution to the original differential equation. So that's how we handle that. Oops. And let's see the last one. Case 3 is very similar. If r1 and r2 are not equal to each other, but their difference is an integer, then y1 and y2 can be constructed in this way. You find y1 the way we talked about already. And then for y2, you assume that y2 has this form, and you'll differentiate twice. You'll substitute into the equation. And because y1 is a solution, often the terms involving y1 cancel. Or the terms involving the y1 multiplied by the natural log of t, or y1 prime multiplied by natural log of t, or y1 double prime multiplied by natural log of t. All of those you can group together, and typically they cancel. Okay. And then the fourth case, the one that we're not covering, is when you have complex conjugate roots. Now, there are a couple of tips down here. If r1 and r2 have a difference that is an integer, and they're not equal to each other, so it's not the integer 0, but it's some other integer. Whenever you do this, it's best to start the iterative process with the larger of r1 and r2 first. So if you get r1 equals 3 and r2 equals, or if you get two roots and one of them is, let's say 1 and the other one is 3. So they're not the same and their difference is an integer. You'll want to start with r1 equals 3 rather than r1 equals 1. Just pick the larger one to construct your y sub 1. And then you'll use, and then this second one, the r sub 2, that's what will be substituted over here in case 3. You've got t raised to the r sub 2 times this series, which is just this series plus an extra 1. Okay, so I hope that helps. I am going to get started on the second solution and a little bit of the third solution, just so that you can see what it is that I just talked about, so they can actually see it in action. Okay, so for the second differential equation. We have t squared times y double prime plus 3 times the quantity t plus t squared closed quantity times y prime plus the quantity 2t plus 1 closed quantity times y equals 0. And I'm not going to spend the time showing that t equals 0 is a regular singular point. I think that you can do that just using the definition and those limits that are shown in the notes. But I will show you how to find the values of r for problem number 2. And then I'll show you basically how to get started. So here's our differential equation. Assuming that t equals 0 is a regular singular point, we're going to let y equal the sum as n goes from 0 to infinity of a sub n raised to the t, or a sub n times t to the n plus r, So we always start that way when we're dealing with t equals 0 being a regular singular point. Now we'll compute the first and second derivative. We'll bring our constant down, and then you've got t to some power. The derivative of t to some power is that power times t to the 1 less power. Now, when we're taking the derivative, when we're just using series solutions about an ordinary point, usually the value of the index increases by 1, because when n equals 0, if there's no r here, we would get a 0 for our first term. But if there is an r here, this isn't necessarily 0. So we're going to start, we're going to keep the n equals 0 here as we take the first derivative. If we take the derivative again, we're still going to keep that 0. Bring the power down, multiply by t to the 1 less power. Okay, and then we substitute into the differential equation. Now I would recommend distributing the t squared, distributing the 3t and the 3t squared to the y prime. Just distribute everything. So I'll have t squared y double prime plus 3t times y prime plus 3t squared times y prime plus 2t times y plus y equals 0. So there are actually going to be 1, 2, 3, 4, 5 series expressions there. Okay, now let's substitute in. We're going to have the sum as n goes from 0 to infinity. This is y double prime of a sub n times n plus r minus 1 times t to the n plus r minus 2. But we're multiplying that by a t squared. So when I multiply this expression by t squared, I end up adding 2 to that exponent. So that's that first piece. For the 3t times y prime, I will multiply by the 3, and then I'll write the expression for y prime right here. This is the sum as n goes from 0 to infinity of a sub n times n plus r times t to the n plus r minus 1. But I'm multiplying it by a t. So if I take 3 times y prime and I multiply that by a t, that's going to add 1 to all of those exponents. Now this one's going to be very similar because I'm multiplying by 3t squared this time. But since I'm multiplying by 3t squared rather than t to the first, multiplying by this series by a t squared adds 2 to all of those exponents. And then I want to have 2 here, and I've got t times y. Y was a sub, the sum as n goes from 0 to infinity of a sub n times t to the n plus r, and I'm multiplying by an extra t, so I want to add 1 to that exponent, and then we'll just add y. So when you do this, you're going to do pretty much the same thing that you did with a series solutions about an ordinary point. We've got these 1, 2, 3, 4, 5 series that we need to add together. And in order to do that, we need to not factor out, but remove terms from each of the series, or from series as necessary, so that the resulting series all start with the same power of t. So when n equals 0, this one starts with n plus, or t to the n plus r. Or when n equals 0, it's going to be t to the n plus r, but n is 0, so that'll be t to the r. The 2 and the negative 2 reduce. Now when n equals 0 here, the 1 and the negative 1 reduce. So this will also start with a t to the r. Now the 1 and the 2 give me a negative 1 and a 2 give me a 1. So when n equals 0, I'll have t to the r plus 1 for that one. For this one, when n equals 0, this will start with t to the r plus 1. And when n equals 0 here, this one starts with t to the r. So these guys start with t to the r plus 1, and these guys, the first, second, and fifth series, they all start with a t to the r term. So I'm going to take out a single term from this guy, and this guy, and that's going to give me my indicial equation. So let's do that. We're going to remove terms from the first, the second, and the fifth series. So that all series start with a t to the r plus 1 power. It'll be a t to the r plus 1 term. It'll be t to the r plus 1 times something. Okay. So the first series, when n equals 0, I'll write that down here. I'll have a sub 0 times r minus 1. And if n equals 0, that'll be a t to the r. And then I'll pick up where I left off. It's going to be exactly the same, but rather than starting at n equals 0, since I removed the n equals 0 term, I'm going to start with n equals 1. Okay, so that's our first series. Now the second series also starts with t to the r. So we want to remove the t to the r term. So we'll substitute in n equals 0. When we substitute n equals 0 there, we have 3 times a sub 0 times r times t to the r. And then we'll pick up where we left off at n equals 1. Okay, so that's the first series and the second series. And the third and the fourth already start with a t to the r plus 1. So we can just write those down. Not really doing anything there. Now for this last one though, that starts with a t to the r. So we'll take out the n equals 0 term. When n equals 0, we have a sub 0 times t to the r, and then the rest of the series looks exactly the same, but we just start with n equals 1. Okay, so we group these guys together. The terms outside our series. We're grouping this one, and this one, and this one. We're factoring out the a sub 0, assuming that that's non-zero. We're factoring out the t to the r and assuming that that's non-zero, and that's going to give us our indicial equation. So if I take out the a sub 0 and the t to the r, from here I have r squared minus r, if I distribute that r. From here, if I take out the a sub 0 and the t to the r, I'm left with a positive 3r. From here, if I take this out, well, this times 1 would give me that. And then we've got the other 5 series. And I'm not going to write them all. I'll just write them like that for right now. The sum of those 5 series, and we get 0. So this is our indicial equation. r squared plus 2r plus 1. Since this sum is 0, this needs to be 0, assuming that a sub 0 is non-zero and t to the r is non-zero, so that's just saying that t is not equal to 0, at least for the moment, then this would have to be 0. And that factors to r plus 1 squared, so r1 and r2 are both equal to -1. That means we're in case 2. So to find y1, we will let r1 equal -1, and then we will find the values of a sub n. So if r is equal to -1, that means this will be 0, and all we'll be left with are these 5 series, and then we substitute r equals -1. So I've got r equals -1 here, and here, and here, and here, and there. So if r equals -1, we'll have, for our first series, this expression will be the sum as n goes from 1 to infinity of a sub n times n plus r, which is -1, so that's going to be n minus 1. And then we've got n plus r minus 1, since r is -1, it's going to be n minus 1 minus 1, which is n minus 2, times t to the n minus 1. So I'm just replacing the r's with -1 everywhere. The next series is the sum as n goes from 1 to infinity of 3 times a sub n times n minus 1, t to the n minus 1 here. The next 2 series, I'm just replacing r with -1. I'll have n minus 1 times t to the n minus 1 plus 1, which is going to be t to the n. Here, I've got the 2a sub n. If r is -1, -1 plus 1 is 1, or excuse me, -1 plus 1 is 0. So this is just going to give me a t to the n. And then that guy is gone because the indicial equation is satisfied. So if r is equal to -1, this whole piece disappears and the highlighted parts are gone. They've zeroed out. And so we'll just have this expression now evaluated at r equals 1. The sum as n goes from 1 to infinity of a sub n times t to the r minus, or t to the n minus 1. So that's our 5 series. Okay. And then you're basically going to proceed in the same way that you proceeded with series solutions about an ordinary point. You want all these exponents to match. You've got a t to the n minus 1 here, here, and here, and these are both t to the n's. Well, since we've got 3 of them that match, it's easiest to make these guys look like those 3. So you'll make a substitution, and that's going to allow you to find your a sub n. So you'll do that. Now, remember what you were asked. Here's your problem statement. It says, solve that equation to find the exponents at the singularity, referring to the indicial equation, then construct the general solution of the given differential equation, or it's a general solution of the given differential equation, from 2 linearly independent solutions. In each case, compute the first 5 non-zero terms of the corresponding series and indicate the interval in which the series are guaranteed to converge. I'm not going to worry about the interval of existence. I'll let you read the notes for that. But I wanted to point out that you're only asked to find the first 5 non-zero terms of these series. So what you're going to need here is a sub 0, a sub 1, a sub 2, a sub 3, a sub 4, and a sub 5, provided none of those are 0. Or a sub 0 through a sub 4, provided none of those are 0. If some of them happen to be 0, then you will have to compute more terms until you find 5 that aren't 0. So that will be how you find your y1. Y1 will be the sum as n goes from 0 to infinity of a sub n times t to the n plus r, where r is equal to -1. So that's what you'll do. It's going to be just like you did. It's going to be very similar to what you did when you were solving problems using the series solution about an ordinary point method. Now, since we're in case 2, our second solution has the form y sub 2 equals y sub 1 times natural log of t plus the sum as n goes from 1 to infinity of b sub n times t to the n plus r1. So this is what we're dealing with. And r1 is, of course, -1. So we're saying y sub 2 is y sub 1 times natural log of t plus the sum as n goes from 1 to infinity of b sub n times t to the n plus r1, where r1 is -1. Okay, so that is our solution, and we want to find the b sub n. In order to find the b sub n, we're going to do what we pretty much always do. Once we know the form of the solution, we'll differentiate it twice, and we'll substitute into the differential equation. Well, and we'll substitute into this expanded form of the differential equation. So we'll have 1, 2, 3, 4, 5 expressions involving infinite series. So let's do that. And this is what I was talking about earlier. When you compute y sub 2 prime, you don't actually want to substitute in the y sub 1 that you already found here. Just leave it as y sub 1. So when I compute y sub 2 prime, I'll have this derivative, or the derivative of that product, excuse me, which can be found by the product rule. So we'll have derivative of the first times the second, plus the derivative of the second, which is 1 over t, times the first. And then over here, well, the sum as n goes from 1 to infinity of b sub n, bring the power down. Excuse me. Multiply by t to the 1 less power. Okay, so now we're there. And if you want, you could even call this t to the -1 times y sub 1. Notice that when n equals 1, we actually get a 0 here. So maybe we should start at n equals 2. Okay, now for y sub 2 double prime, use the product rule again. We'll have product rule here. Derivative of the first times the second, plus the derivative of the second, which is 1 over t, or t to the -1, times the first, plus here, use the product rule again, derivative of the first by the power rule, times the second, plus the derivative of the second, times the first. And then the series, well, the sum as n goes from 2 to infinity of b sub n times n minus 1. Use the power rule. That's going to be n minus 2 times t to the n minus 2. But when n equals 2, we get a 0. So let's start with n equals 3. And notice that this is a like term with this one, so you'll have 2 of those. After you've done all of this, you're going to substitute these guys into this differential equation. And then you're going to simplify as much as you can. Now, because y sub 1 is a solution to this equation, when you group the natural log of t terms together, these cancel. Most of them cancel. So let's actually work that out. I don't want to do all of your extra credit for you. But the differential equation looks like this. This is my y sub 2 double prime. When I take this and I multiply by a t squared, what I get is this. This times t squared is t squared y sub 1 double prime times natural log of t. This and this, they're the same. I've got 2 of them. So that's 2 over t times y sub 1 prime. We're multiplying that by t squared as well. So one of those t's will reduce. So we've got a 2t times y sub 1 prime there. And then if I multiply this one by t squared, I've got a t squared in the denominator, a t squared in the numerator. So I'll just end up with a negative y sub 1. And then this times t squared, it's just the sum as n goes from 3 to infinity of b sub n times n minus 1 times n minus 2. And this times t squared is just going to give me a t to the n. So that is my first expression right there. And I've got to do this 1, 2, 3, 4 more times. So I have 3t times y prime and y sub 2 prime, which is right here. If I multiply this by a 3t, I've got 3t times y sub 1 prime times natural log of t plus 3t times this. I'll have a t in the denominator, a t in the numerator. It's just going to give me a 3 times y sub 1 plus this series. I'm multiplying it by 3t, so I'll just put a 3 inside. And if I multiply this by a t, I'm just going to add 1 to the exponent, n minus 2 plus 1. It's going to give me an n minus 1. Then I want to add 3t squared times y prime. So 3t squared times this expression here. It's going to give me a 3t squared times y sub 1 prime, natural log of t. And 3t squared times this is going to give me a 3t times y sub 1. And 3t squared times that. Put a 3 inside my summation. If I take this and I multiply by a t squared, I end up with a t to the n. Okay, so we've taken care of this guy and this guy. Now we need a 2t times y and a y. So this is my y sub 2. I want 2 of those. Or 2t times that, excuse me. Put the 2 inside my series. If I multiply this by a t, I just end up with a t to the n. Okay, so that's 2t times y. And then I want to just add y onto this as well. So I have y sub 1 times natural log of t plus this sum as n goes from 1 to infinity of b sub n times t to the n minus 1 equals 0. Okay. Now, remember what I told you about those natural log of t terms and the y sub 1 terms. Y sub 1 is a solution to this differential equation. So if I replace all of these y double primes and y primes and y's with y sub 1 double prime and y sub 1 prime, this will give me 0. Notice that in this column right here, that's exactly what I have. I've got, if I factor out the natural log of t, I've got t squared times y sub 1 double prime plus 3t times y sub 1 prime plus 3t squared times y sub 1 prime plus 2t times y sub 1 plus y sub 1. So this column, if I just add those together, is this times natural log of t. But since this evaluated at y sub 1 equals 0, that means all of these guys are gone. These cancel because y sub 1 is a solution to the differential equation. So you might say, well, what do we have left? Well, then we have a 2t times y sub 1 prime minus y sub 1 plus 3y sub 1. So that's going to give me plus 2y sub 1. Taking care of this one, and this one. Then I've got a 3t times y sub 1 there. Plus the sum of 1, 2, 3, 4, 5 series. Equals 0. Now, this is where you actually will substitute your y sub 1 now. You know what y sub 1 is. You know the first 5 non-zero terms of y sub 1 because you already found the first 5 non-zero terms of y sub 1. I actually recommend finding the first 6 non-zero terms of y sub 1 because you're going to have a y sub 1 prime here. So This sum of 5 series can be written as a single series involving your b sub n. On the other side, you're going to have, if you move all of these to the side, you have negative 2t times y sub 1 prime plus 2 plus 3t, all multiplied by y sub 1. Or actually, it might be better to leave that factored. Since you know what y sub 1 is, you can compute that derivative term by term, and you can substitute in that y sub 1, all 5 of those non-zero terms. And then you're going to have an expression involving t over here. This will eventually be a constant plus a constant times t plus a constant times t squared plus a constant times t cubed and so on. But these constants will be known. You're going to have numbers here because you know what y sub 1 is. The only way the series on this side is equal to the series on this side is if the corresponding coefficients on this side equal the coefficients on this side. So the constant term over here will have to equal the constant term over here. And the t term over here will have to equal the t term over here. And the coefficient of t squared on this side has to equal the coefficient of t squared on that side. And that is going to allow you to find these b sub n's. And once you have the b sub n's, we want the first 5 non-zero terms of that those b sub n's. You can substitute that here, and that's going to give you your y sub 2. Okay, so that is how we handle that second case. Now for problem 3, I don't believe it's case 2. I don't know if it's case 1 or case 3. It's probably case 3. But case 3, you're going to handle it in pretty much the same way. First, you'll find out what your R1 and your R2 are. If the difference is an integer and they're not the same, you'll let y1 equal this, and then remember to follow this instruction. It's best to start with R1 being the larger one. So whichever number is larger here, call that your R1 and find y sub 1. And then once you do that, you're going to assume that y sub 2 equals this is the solution of the differential equation. You'll differentiate twice, substitute into the equation. Because y sub 1 is a solution, all the terms involving the y sub 1 multiplied, or y sub 1 and y sub 1's derivatives multiplied by the natural log of t will cancel. And you'll end up with something similar to what we ended up with over here. Where after you substitute, you're probably going to have some series outside, and then in terms of y sub 1, and then you'll have some series that you're trying to find involving the b's. You add the series involving the b's together on one side, and then you move the other expressions to the other side, and then you just do what we've been doing all semester. Because of the linear independence of 1, t squared, t to the third, t to the n, for different values of n, because of that linear independence, the only way that the expression on this side can equal the expression on this side is if the coefficients of the expression on the left are equal to the corresponding coefficients of the expression on the right. That's going to be enough to find the b sub n's. So I know it's a lot. That's why it's extra credit. I hope that that video helps you. I wanted to give you at least one concrete example. And again, during the spring 2021 semester, you have until the day after the final at noon in order to get this in. Sorry, I was busy yesterday and I wasn't able to get to this until just now. So please let me know if you have any questions about this. And I wish you the very best of luck on your exam. I hope you're doing great right now. And I'll talk to you soon.